Hi, welcome to your first flip video of Topic 6. Topic 6 is called Decimals and Percents, and it's part of Unit B. Unit B is made up of Topics 4 and 5, which we've worked on since, late November, and now we're going to start Topic 6. So Topic 6 is Decimals and Percents, so it really ties into what we've been working on with Topics 4 and 5. So 6.1 is the first section of Topic 6, and it's called Repeating Decimals. 6.2 is called terminating decimals, and really the heart of this is what is a repeating decimal, how do you compare repeating decimal values. So let's start there. What is a repeating decimal? Well, a repeating decimal is a decimal expansion that repeats the same non-zero digit or block of digits without end. So there's a lot of information packed into this definition. Let's start with that non-zero. So let's say you have the number 4. 4 is the same thing as 4.000, however many zeros you want to put in, because those zeros don't influence the value of that 4. 4 is the same thing as 4.0, which is the same thing as 4.00, which is the same thing as 4.000, which is the same thing as 4 with a trillion zeros at the end, which is the same thing as 4 with an infinite number of zeros at the end. So we, as mathematicians in the math community, have decided we're not going to write out all those zeros because it would take forever to write out a single number anytime you want to do a problem. But all those zeros are there. So what's what they throw that caveat of having a non-zero repeating at the end, because technically every number has a 0 repeating decimal at the end, but it doesn't change the value. So it's not in that category. It's the exception. All right. Now, if it has a digit that repeats, so for example, 0.3 repeating, and we represent that repeating on for forever with a bar over the digit or digits that go on forever. So in this example, only the 3 repeats. In a second we'll look at another example where it's 2 numbers that repeat. But 0.3 repeating, and that's how you read that number, 0.3 with a bar on top of it means 0.3 repeating, which means 0.3, but those 3's go on forever and ever and ever. And I can't continue writing out all the 3's. You could literally fill up from now until the end of time writing out all those 3's because they never stop. There's an infinite number of them. So we represent that going on with the 3 dots. So you can have a repeating decimal with just a single digit, in this case 3, repeating on forever and ever and ever. But you could also have a block of digits. So I'm going to show you a 2 block, so 0.54 repeating. And the bar, notice, is not just over a single digit like it was in 0.3. It's over the 5 and the 4. So what does this mean? It means 5.4 repeats the numbers 5.4. So not just the 4, not just the 5, but 5.4, 5.4, 5.4, 5.4. Goes on and on and on in this pattern forever. You don't have to only have a 1 or a 2 digit repetition. It could be, a 3, 4, 5 digit repetition. You can have a million digit repetition if that's what the decimal is. You don't see too many of those because it's a very specific fraction that you'd have if you have a million digits repeating in an order like that. But you can technically have them. There is no upper limit on how many digits repeat. And again, notice those 3 dots because I can't possibly write out all those 5.4s, all right? So how do you determine if a fraction is a repeating decimal? Well, 2 over 9 really means 2 divided by 9. So we can use long division, a skill we honed in on in topic 5, to divide the to turn this fraction into a long division problem and then solve it like that. So 2 divided by 9, can't pull a 9 out of a 2, so let's make that 2.0. Well, you can pull a 9 out of a 20, pretend the decimal's not there, and then use bring it on up in your answer later on. So how many times does 9 go into 20? Well, 9 goes into 2. 0 times 9 times 0 is 0. 2 minus 0 is 2. Bring down the 0. 9 goes into 20 how many times? 2 times. 9 times 2 is 18. 20 minus 18 is 2. Bring down another 0. And now I'm going to bring up my decimal, so 0.2. And I did that because I already know I'm done. So it's 0.2 repeating. Now, how did I know that I was done? Well, you see these 2's? I have had the same remainder 2 consecutive times And all I'm doing is now adding zeros. I have already exhausted the 2 that was given to me at the beginning with the 9 goes into 2 0 times. So it's that first step. So I could keep going, and I'll show you all the long division for that, but I'm always going to get these remainders of 2. So all those 2's up in my long division are that there's no point in writing them because I can easily represent them with a bar over my 0.2, my 2 tens, to show that those 2's go on forever. So a quick, easy rule to help you to know when you are done and you definitely have a repeating decimal is to look for the same remainder or same repeating pattern after you start adding zeros, because once you start adding zeros, you're not influencing the value of the number. Now, if you had the number 1, 2, 3, 4, 5 divided by, let's say, 11, and you just happen to get the same remainder of 3 after the first step and the second step, you don't know if you're done because you haven't exhausted all of those digits of the number. Now, if you had 1, 2, 3, 4, 5, 6, and then you did 0.0, and then got a remainder, and then did another 0, got the same remainder, after 2 of those, you're just adding zeros at that point. The value of the number is not changing. You have exhausted the digits, so you know that those digits from there on out have to be repeating, all right? So we can look at an example where you see this repeating pattern. So if you have 2 over 11, that means 2 divided by 11, and I've already made it 2.0, because I know 11 can't go into 2, so how many times can this work? Well, 11 goes into 2 0 times. 0 times 11 is 0. 2 minus 0 is 2. Bring down the 0. 11 goes into 20 one time. Now 20 minus 11 is 9. Bring down a 0. 11 goes into 90 8 times. 88 is 8 times 11. 90 minus 88 gives me 2, and I am already starting to see a pattern. Bring down a 0, I'm back at 20. How many times does 11 go into 20? 11, one time, which 11 times 1 is 11. Subtract 9. I see this pattern emerging. I have a remainder of 2, remainder of 9, remainder of 2, remainder of 9. So if I bring down the 0 and 90, how many times does 11 go into 90? Well, 8 times. So I have 88 again, and I've ran out of room. But you'll notice, you have this point, and I don't have that 0 in there. Let me add it really quick. You have 0.1818, and I'm getting this repeating pattern, so I can represent this as 0.18 repeating, okay? So look for these patterns. You're looking for either the same remainder or these remainders where they alternate. 2, 9, 2, 9. There would be a 2 down here, but I've run out of room, and that pattern will go on forever because the 1/8s go on forever. Now, I'd like to just make a quick little note. These 3 dots up here that I've used a couple of times, we approached a problem in class where is this a repeating decimal? And I think the exact scenario we had from class was 0.172 ... Now, this is not necessarily a repeating decimal, and why is that? Because the numbers continue, that's what the 3 dots represent, but they may not be 2s, you know? You might have 1.72222225. There might be a 5 or another number, 10 digits down the line, or 100 digits down the line, or 1,000 digits down the line. These dots just mean the numbers continue. The bar over the number means that that specific number continues. So 0.3 with the bar on top means that those 3's continue forever. 1.72 ... means that the decimal continues. It doesn't stop at that 2, but it may not necessarily be only 2's after that number, okay? So this is why. So, for example, we've talked about pi a couple of times. It was in the movie we watched. Pi is 3.14 ... There are a whole bunch of other digits that go after pi. Pi is, I think as of 2013, a trillion digits calculated, and we don't think that there's a pattern, and we know that pi never stops, but we haven't established a pattern, and we don't know if there is a repeating factor within pi. So we can't say for sure that pi is not a repeating decimal because we haven't reached the end of pi and no one has mathematically been able to prove that there is no pattern or that it might not repeat at some point. So those dot dot dots don't mean that it's repeating, it means it continues, and that's a big distinction because 0.3 with a bar over it, 0.3 repeating means those threes repeat. 1.72 dot 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 means there's just more numbers. It's not necessarily a pattern or a block of repeating numbers. So just a little caveat there. So let's work on this. You have a table of fraction values on the left-hand column, 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3, 6 over 3, and 7 over 3. And the right-hand column is blank. We're going to fill in the decimal values. So if you have 1 over 3, let's start there. That means 1 divided by 3. So if I expand 1 to 1.0, how many times does 3 go into 1? 0 times. 3 times 0 is 0. 1 minus 0 is 1. Bring down the other 0. 3 goes into 10. Okay, let's bring up my decimal point at the beginning. 3 goes into 10. 3 times 3 is 9. Subtract, I get the 1. Oh my god, look, I have already a repeating decimal, or a repeating remainder. You know, I already know that I'm done at that point. Let's keep going for a couple more. So if I bring down another 0, I'm at 10. And I see now I have this pattern. I will always have this remainder of 1 because I'm always going to get a 10. And then how many times does 3 go into 10? 3 times, get a 9. 10 minus 9 is 1. Whole cycle repeats itself. So 1 over 3 is 0.3 repeating. Now, if you know 1/3 is 0.3, then 2/3, how do you get from 1/3 to 2/3? Well, you multiply by 2. And we can show this using fraction multiplication. 1/3 times 2 is the same thing as 1/3 times 2 over 1, because 2 is the same thing as 2 over 1, and you guys know how to multiply fractions. You multiply numerator by numerator, denominator by denominator, so 1 times 2 is 2, 3 times 1 is 3, so 1/3 times 2 is 2/3, and that makes sense. If you have 2/3 is twice as big as 1/3. So if I multiplied my fraction by 2 to get my new fraction of 2/3, then I should be able to do the same thing with my decimal. So if I do 0.3 times 2, I can rewrite it as 0.3 times 2 in the vertical format, and 0.3 times 2, 2 times 3 is 6, and then I have 1 space behind the decimal point, so I'm going to take my decimal and move it 1 to the left to represent that 1 from the original 0.3 repeating. So 2 over 3 is equal to 0.6 repeating, all right? So I'm going to fill that in. 0.6 repeating. Now, let's look at, so times 2 times 2. Now, I know that 1/3 times 3, using the same logic we use with the 2/3, means that I should take my 1/3 value and multiply it by 3 to get to 3/3. But I also know, because I'm, you guys are smart enough to do this, 3 over 3 means 3 divided by 3, and what's 3 divided by 3? It's 1, so my answer should be 1. But if you did the multiplication, you'll get 0.3 times 3, which is 9, so 0.9 repeating. 0.9 repeating isn't the same as 1, and it's a very complicated issue. For right now, let's just use the fact that we know that 3 divided by 3 is 1, and on Monday we're going to do a little activity where we look into why do I get 0.9 repeating when I multiply, but I get 1 when I use common division logic. So for right now, just believe and have faith that I will explain this to you on Monday. We'll do a little activity about that. All right, so let's go to the 4/3. Well, how do you go from 1/3 to 4/3? You multiply by 4, so if you do it to the fraction, you should be able to do it to the decimal. So let's look at this. 0.3 repeating times 4. Now if you multiply that, I'm going to show this in 2 different formats, and it's because there's a component here that I really need you to understand. So let's just go 3 decimals out, or 5 places out with the 0.3. So, those 3's go on forever, but let's just look at 5 of them. So 0.3 times 4, 3 times 4 is 12. I got 1 space, so I take my decimal, move it 1 to the left. 0.3 times 4 is 1.2. Now, any of you who are good with decimal approximations already, you know this isn't true. So let's look into why it's not true. So let's look at the other example. 4 times 3, I'm going to highlight in red just to remind us that this is not technically correct. Now let's look at the other example. 4.3333 times 4. 3 times 4 is 2, carry the 1. 4 times 3 is 12, plus 1 is 13, carry the 1. Same thing, 13, carry the 1, 13, carry the 1, 13, nowhere else to carry, so I'm done. So let's count how many spaces I have. I have 1, 2, 3, 4, 5. So I'm going to take my decimal point and move it over 5 spots. So I get 1.33332. Now, you know, if you're good with decimal approximations, that 4 over 3, or 1 1/3, should be 1.3 repeating. So why is there that 2 at the end? Well, you have to remember, so I'm going to do this in gray, that there are 3's that go on forever after that 5th 3 that I wrote out in green. So really, there's always going to be a 3 to the right to carry the 1 to make that 2 into a 3. So you have to remember those 3's go on for an infinitely long length. So at the end of an infinitely long length is this 2, but because it's infinitely long, there's no way for you to ever access that number. All right, so let's keep moving. So again, that 2 is always going to be a 3. That 2 is always going to be pushed back infinitely towards the end of this decimal. So 1.33333, an infinite number of 3's, and then this 2, which is always going to be rounded up, gives me 1.3 repeating. So 4/3 is equal to 1/3 plus 3/3, which is 1 plus 0.3 repeating, which is 1.3, which is what we just got. So we know that 1.3 repeating has to be my answers, and the 1.2 repeating can't be right. It's too rough of a calculation. So 4/3 is the same thing as 1.3 repeating, and we can use the same logic of doing, 5/3 is 2/3 plus 3/3, so 1 plus 2/3, and I know 2/3 is 0.06. We calculated that up here, so we can go ahead and say this is 1.6 repeating, 6 over 3 is 2, and this really ties into that, why is 3 over 3 1, but 1/3 is 0.3, and 0.3 repeating times 3 gives me 0.9 repeating, and we'll look into that. So it's the same idea again, and then 7/3, 2 1/3, so 3 over 3 plus 3 over 3, which is 2, plus 1/3, so 2 plus 0.3 repeating, so 2.3 repeating, okay? Last thing in 6.1 is comparing a decimal value and a fraction value and determining which one's larger and which one's smaller, or if they're equal. So on the left you have 8.7, and on the right you have 8 7/12, and we're going to determine if it's less than, greater than, if 8/7 is less than, greater than, less than or equal to, greater than, equal to, or equal to 8 7/12. So I already know exactly how big 8.7 is. It's exactly 8 plus 7/10, so I can use that to solve. Now if I get the decimal approximation, the decimal value of 8 7/12, I can compare those quickly, because you can compare fractions very easily. So 8.7 is the same thing as 8.7. I'll put a 0 repeating after it, because there are an infinite number of zeros after that 7. And now I have 8 7/12, which is 8 point something. So let's figure out what that something is. Well, 7/12 is 7 divided by 12. How many times does 12 go into 7? Let's add the 0 at the end. 12 goes into 7D 5 times, because 12 times 5 is 6D. 70 minus 60 gives me 10. Bring down another 0, 100. How many times does 12 go into 100? It goes into 8. 8 times 12 is 96. 100 minus 96 gives me 4. Bring down another 0, we're at 40. How many times does 12 go into 40? 3 times 12 is 36, and I get a 4. Oh my god, there's my double pattern. I got a 4 and then another 4, so I'm at 40 minus 36 again. 4, 4, 4. Gonna keep going on forever, so this is 5.83 repeating. Now I'm gonna put that bar over that first 3. I don't need to do it over both 3's, because 0.3 repeating means 0.333 forever and ever and ever. 0.3 with a bar over both of them means 33, 33, 33. they're the same number, but it's redundant, it's unneeded to add that second 3 under the bar. So I'm going to get rid of it, and I have 0.83 repeating, with only the 3 repeating. And I'm going to pop that in. So 8 and 7/12 is 8.583, 3 repeating. And now these are easy to compare because decimals, you just line up tenths versus tenths, hundreds versus hundreds, thousands versus thousands. Whichever one has a bigger value is larger. So I'm looking at the tens because that's the first place they differ. 7 tenths for 8.7 versus 5 tenths for 8 and 7/12, which is 8.583 repeating. 7 is bigger than 5, so 8.7 is bigger than 8 and 7/12. Let's try one more, and then we'll conclude the video. 6 and 5/12 versus 6 and 4/10. So 6 and 5/12 is 6 point something. So let's find that point something. 5/12 means 5 divided by 12. Can't pull a 12 out of 5, so let's make it 5.0. 12 goes into 5 0 times. 0 times 12 is 0. 5 minus 0 is 5. Bring down the 0. How many times does 12 go into 50? 4 times. 12 times 4 is 48. 50 minus 48 gives me 2. Bring down another 0. I'm at 20. How many times does 12 go into 20? 1 time. 20 minus 12 is 8. Bring down the 0. I'm at 80. How many times does 12 go into 80? 6 times. 12 times 6 is 72. 80 minus 72 gives me 8, and boom, I have my pattern. I've started throwing extraneous zeros at the end of that 5. So I see 8, I see 8 again. I know that 6 is going to repeat now, so I'm just going to throw my decimal up, put the bar over the 6. 5/12 is the same thing as 0.416, 6 repeating. So 6 and 5/12 is 6.416 repeating. And now 6.4 is 6.40 repeating at the end. So let's compare. Well, the 6's are the same, the 0.4's are the same. Now we're going to look at 1 versus 0. 1 is bigger than 0, so 6 and 5/12 has to be bigger than 6.4. I know this is a little bit of a lengthy video, but there's a lot of concepts in here that make repeating decimals a little bit more complex than initially thought of. But this is all that it is. 6.2 will cover terminating decimals, which are decimals that end in a finite manner and don't go on forever. Let me know if you have any questions.